So, by now, you should know where all of these mountain ranges listed are located. Let's talk specifically about the Rocky Mountains. So, the Rocky Mountains obviously are in Western Canada and Western US. They kind of range all the way down here. And when you looked and compared that to a plate tectonics map, and I've got a simpler version here, you can see that this is where the Pacific Plate is kind of going underneath or the North American plate. So this would be a convergent plate boundary. We've got the Pacific going underneath the North American. Obviously, there's something funky going on here with the Juan de Fuca plate, but for the most part, it's a convergent plate boundary. Now let's take a look at what those mountains look like. If you've got a convergent plate boundary, what you see often is these very sharp young mountains. Most of the world's mountains occur in these long belts, up to thousands of kilometers long, and they're along these convergent plate boundaries. The Rockies, the Andes, the Himalayas, all of them are along convergent plate boundaries. And here we've got the Rocky Mountains just outside of Calgary, and this is in Idaho, just south. You see, you've got these very sharp, jagged, pointy mountains. They look like what you think mountains should look like. You also should have found the Appalachian Mountains. So the Appalachian Mountains are on the east coast of North America, kind of just if you drive into Lake Placid, that sort of area, just east of Montreal. You've got these mountains that go all the way along the east coast. Well, when we look at our map of plate boundaries, that's like right here. That's absolutely nowhere close to a plate boundary. So there's got to be something else going on there. When we take a look at what those mountains actually look like, well, this is what standing on the Appalachians look like. This is all in upstate New York. There's me standing on them. And you see that we don't have those rugged mountains anymore. Instead, they're very rounded. They're, well, shorter, smaller. They don't have the same elevation. And this is true for mountains that aren't on current plate boundaries. And the reason they're so rounded and so much, will have so much less relief, is that they're really, really old. They were once on a plate boundary, but they're no longer. Um, Plate tectonics have changed. So that plate boundary that formed those mountains is now millions of years old. So the ones that aren't on plate boundaries tend to have a less jagged appearance, are smaller, or more eroded away. So, to understand how processes at convergent plate boundaries contribute to mountain building, geologists study what happens at the boundary between the continental crust and the oceanic crust. These are called the continental margins, and there's two types of them: active margins that occur along plate boundaries, like where the Nazca Plate meets the South American Plate. And if we take a look at that, we see that's right here. So Nazca Plate meeting the South American Plate. That's an active plate boundary. And the Andes are the mountains formed along here. Then, to compare, we've also got passive margins. So passive margins don't have a plate boundary, like off the east coast of Canada. There, the continent ends and the ocean begins, but there's no plate boundary there. It's in the middle of the North American plate. And let's take a look again at our tectonic plate map to see what I mean. So right here, obviously, our North American plate on the east coast, the continent of North America ends, the ocean begins, but that's in the middle of an entire plate. So that's a passive margin. So mountain building happens at these active plate margins. Passive plate margins or passive plate boundaries are stable, and they tend to accumulate a lot of sediment that's washed off of the continent. So sediment builds up at a passive continental margin. Over millions of years, the mountains or hills that are there are going to erode away. They're going to create a lot of sediments, and rivers and other agents of erosion can carry these sediments to the ocean. These and other sediments are then deposited along the passive continental margins. So a lot of sediment can build up here on the ocean floor. And the sediment at these passive margins can become new mountains over long, long periods of time as the plate boundaries change. For example, the active continental margin off the west coast of South America was a passive continental margin until about 200 million years ago. The Andes, those mountains in South America, now have the sediments that were once deposited on the passive continental margin. So, what actually makes these mountains form? Well, it all has to do with stress. If we've got a convergent plate boundary, well, there's a lot of stress that's applied to the rocks at that boundary. The three types of stress are shown in our little diagram over here to the right. So if you had according to our principle of original horizontality, we know that all of those ocean sediments at a passive continental margin would have been deposited pretty much horizontal. And if you apply some compression stress to that, your rock layers are going to be squeezed inwards. Compression is going to make the rock layers thicker and shorter. It's going to push them upwards, giving you a dome like this. You can also end up with tensional forces. This is what happens if rock layers are pulled apart. Tension tends to make the rocks thinner and longer. And here you can see that if you pull enough, well, some of those layers are going to fracture, and you'll end up with faulting. And then we've got shear stress. This is when the rock layers are pushed in opposite directions. And this will distort the shape of the rock, especially in the plane the plane between the opposing forces. It's also important to remember that things will change based on the type of rock that is being stressed. A layer of shale might tend to fracture and crack, whereas a layer of sandstone would be more likely to fold. And speaking of folds, the Rocky Mountains out in Western Canada exhibit a ton of this folding. Here's a picture from Kananaskis. There's we name two types of folds. An anticline is an upwards fold, and a syncline is a downwards fold. So this part of the mountain here is an anticline, whereas this structure that's folded up is a syncline. So this mountain shows both an anticline and a syncline, and obviously it's gone through a lot of stress. Faults, we've mentioned these multiple times, but to go through in a little more detail, a fault is a break in the lithosphere where movement has occurred. The part of the fault above the fault plane is called the hanging wall. The part below is called the footwall. This diagram will explain a little more thoroughly. So here's my fault plane. The hanging wall is the wall that's on top of the fault plane, and the footwall is the wall that's below. A normal fault, the footwall is moving upwards, and the hanging wall is moving downwards. These occur when you've got tension forces. The rock cracks, and this chunk is moving downwards. So the hanging wall is moving downwards. On the other hand, a reverse fault has the hanging wall moving upwards and the footwall moving downwards. And this kind of faulting occurs when you have compression. So normal faulting occurs when you have tension pulling apart. Reverse fault happens when you have compression pushing together. And then a thrust fault. A thrust fault is a special kind of reverse fault where the fault plane is less 45 degrees or less from horizontal. So these are common in a lot of mountain belts, including the Appalachians. Um, and as a result of these compressional forces, the hanging wall and the footwall can move really large distances. So this is just a special kind of fault. Then we've got the last one, a strike slip fault. This occurs when you've got rocks moving in opposite directions, horizontal to one another. The San Andreas fault is a famous example of a type of strike slip fault. So joints are kind of like faults. They're breaks in bedrock, but no movement has occurred there. So you'll hear that term used occasionally in geology as well. Okay. So then from these folds, we can end up with folded mountains. If you've got two plates carrying continental crust and they collide, um, there's a lot of compression happening there. A lot of compressional forces. Rocks are going to fold and crumple into folded mountains. And there's a ton of examples of these. The Northern Rocky Mountains, like that photo I showed you from Kananaskis, is a great example. The Alps, um, the Himalayas are all examples of these folded mountains. Even the Appalachians, despite the fact they're so old and are no longer at a continental boundary, they're still folded mountains. So Himalayas, though, also a great example as the tallest mountains on the planet currently. So here we had the Indian. So here we have the Indian plate moving towards the Eurasian plate. And for a long time before the Himalayas started forming, the oceanic crust on the Indian plate was being subducted underneath the Eurasian plate. All well and good, just normal subduction going on here. But eventually, all of that oceanic crust was subducted as India moved towards what's currently Tibet. And now two continental plates are colliding. So once that ocean closed, subduction stopped. India and Eurasia collided, and they started crumpling and creating folded mountains, the Himalayas. Well, why didn't the plate keep moving underneath the other plate? Well, keep in mind that both of those continental plates have the same density. You don't have one that is dense enough to be subducted underneath the other. As a result, instead of one going under the other, they both had to push upwards. Okay, our second kind of mountain are dome mountains. These are nearly circular folded mountains, and they're not found in mountain belts. Instead, they're isolated structures, and they tend to occur in areas that are pretty flat of sedimentary rock, and that might have bent upwards as a result of uplifting forces. There's a couple types of these. So one is the tectonic dome mountains. These result from uplifting forces that arch rock layers upwards. And the second is the plutonic dome mountains, which form when overlying crustal rocks are pushed upwards by an igneous intrusion. So tectonic dome mountains, I think the Black Hills of South Dakota could be classified these, or the Bighorn Mountains in Wyoming. But plutonic dome mountains are pretty interesting looking. This is what's known as Devil's Tower in eastern Wyoming. It really is. It seems to be just in the middle of the flat prairies. And then you've got this plutonic dome sticking out of the prairies. It's crazy. And it's all made of granite. So you see these granite tower, or this granite tower sticking out of the prairies. Okay, so those are other examples of types of mountains. Then we have volcanic mountains, and these tend to form near a subduction boundary or over hotspots, essentially just giant volcanoes. Think of Mount Doom from Lord of the Rings. So that's a example of a volcanic mountain. And then fault block mountains. The Tetons in western Wyoming are an example of fault block mountains. And these aren't formed by compression. Instead, it's primarily tension forces that create these kinds of fault block mountains. So some parts of the U.S., the Earth's crust is being pushed up slowly, and this uplift has caused the crust to stretch and to crack, and this forms faults along the surface. As uplift continues, whole blocks of the crust have been pushed upwards into these fault block mountains. So you get these very angled, very triangle shaped mountains, exactly kind of the way a 10-year-old kid would draw mountains. And the last feature I want to talk about are horse and grabens. And this is particularly relevant for Ottawa's geology. Tensional stress and normal faulting also results in these horse and graben features. And the Ottawa River Valley is an example of a graben. So, along the Ottawa River Valley, this is actually a failed rift valley. So, tensional forces started pulling apart the two sides of the river valley, and the valley dropped below, creating this graben. A horst is the opposite process, where the sides are pulled out and the top is raised. Um, so the Ottawa Bonshare Graben falls all the way along the Ottawa River from Ottawa upstream. And this big valley makes for great lookouts. If you've ever gone up to the Champlain Plain Lookout in Gatineau Park and you look out, you're looking across the Ottawa Bonshare Graben. And if it's a clear day, you can see all the way across to the other side. Places like Calabogie or the other ski hill over there are the other side of the graben. The whole valley floor has dropped down because of tension pulling the two sides apart.